This question is about combustion of methanol. These were taken from Felder, third edition, problem number of 4.71. Here we are going to learn about this extent of reaction method and atomic balance method. Here, the problem statement is liquid methanol having a density of 792 gram per liter is fed to a space heater at a rate of 12 liter per hour and burned with excess air. The product gas is analyzed and the following dry basis mole percentages are determined, which is methanol or is a dry vapor and CO2 and CO. So these are all only the dry gas constituents, which means there will be some moisture also present. Okay. Calculate the percentage conversion of methanol. That is, we need to find the conversion of methanol and percentage of excess air fed and water in the product gas, which means service here they are reporting only the dry gas contents and what moisture content is to be found also. Okay, so we need to find of course I just gave the answer here itself, so those who want they can also try. Okay, that's what is the idea. And calculate the molar flow rate of the dry product gas. For this rate of 12 liter per hour, we need to find the molar flow rate of the dry product gas, that is excluding water vapor, and that of water vapor. Okay. Okay. Now, in this problem, of course, though there is a requirement of calculating the data for 12 liter per hour, first I am taking this base of 100 mole of dry flue gas. Now, why it is? Because we have the specification here. This is about the product gas leaving the heater. Okay. So here we have this methanol content, CO2 content, CO content. Of course, the total is not adding to 100. Why it is so? Because there will be O2 as well as N2 as well. Because we are using excess air. So definitely O2 will also be there in the product. As well as N2 is there because it is we are using air for the combustion. So that contents also we have to find. Of course, based on this data, we can find that. Let us see how they are calculated. And here, we need to find the conversion, excess air, and percentage of water in the product gas. Okay, so these are okay. What are the reactions possible here? Here, since CO2 and CO are there, or is methanol is not only undergoing reaction as per the complete combustion, it is also going incomplete combustion turning to CO. Or is methanol giving rise to CO2, methanol also going to CO. Or is this thing is happening because of incomplete combustion. Okay, so these two reactions are possible. So based on this, we can easily say that we'll be having CO2, CO, water vapor in the product, and O2 and N2. These are all the constituents of the leaving gas. Okay. So here the dry flue gas content is given, which is 0.45% and 9.03 and 1.81. So I am taking this 100 mole of dry flue gas, or this total dry flue gas is 100, which is 0.45 methanol and 9.03 CO2 and CO. So these are all already given. And additionally, O2 and N2 also supposed to be available. So, okay, let us not worry about this now. O2 will be, how much of O2 will be there? Okay, before that, how much of N2 will be there? Air, say, let us take this A as air and M as methanol. And N2 of air will be 79%, 0.79 of A will be your N2. So N2 is coming only because of this air entering. Okay, N2 amount is available. And O2 will be, how much of O2 will be leaving and how much of, and what are all these things for that. And we know this terminology, or is moles of a constituent equal to what is initially present. So or is moles, or is this applicable for the reacting system. So moles leaving equal to moles entering and plus what is getting produced or what is getting consumed. So of course this thing you can easily see in our chemical reaction equilibria of this Smith and Vaness thermodynamics. Okay, so Ni, there is a component, moles of a component equal to moles of a component initially available plus what is getting produced or what is getting consumed. So for methanol, M is initially available. Okay, that is entering. Of course, methanol is getting consumed in both reactions. So this nu will be actually -1. Nu is actually stoichiometric coefficient. Stoichiometric coefficient of the products are positive, or is this is 1 CO2 and 2 H2O, 1 CO and 2 H2O. And stoichiometric coefficient of the reactant will actually take it as negative. Otherwise, this nu I for the first reaction, no, J refers to the reaction number. So nu I for the first reaction is -1, and nu I for the second reaction, or is for the methanol, is also -1, whereas that of O2 is, here it is -1.5, it is -1. Okay, so I will come to that. Say the uh, methanol in the product is, methanol in the product, that is Ni, N of methanol in the product equal to N methanol present initially minus, oh, it is minus because this thing, this nu I is -1 for the first reaction, and again -1 for the second reaction, minus of EJ refers to extent of the reaction. So extent of first reaction and extent of second reaction. So we are having this -1 because of -1 here, -1 here. That is for the reactant, we'll take it as minus. For the product, it is plus. Okay. So by this way, we can write methanol in the product is M minus E1 minus E2. Like that, CO2 in the product is, CO2 is coming there in the first reaction alone. So here, this is having a stoichiometric coefficient of 1. So N naught is actually 0 for that. And stoichiometric coefficient is simply 1. And it is for the first reaction, extent of first 1. Like that for the CO, it is 1, and the extent of second reaction, that's why E2. There is no CO present initially. That's why there is no content like this. So E1, A2, like that. O2 in the product is, O2 initially present is 0.21. There is molecular O2 entering. Molecular O2 entering is 0.21 into A. There is 21% of A. And what is getting consumed, or the first reaction, it is -1.5 E1. And for the second reaction, it is -1. That's what is given here. Okay. So now we have written these things based on the given data, as well as from this usage of this formula, which is moles at moles for moles of a constituent is initially initial moles present plus what is getting consumed or what is getting produced. Okay. So from that, we are having these equations as well. Now we can easily say like what is E1, what is E2, and from that even we can also calculate M as well, because this reaction, this equation is coming from this balance for methanol, which is methanol in the product is 0.45. So that is also having this equation. So from that, and E1, E2 are available here. Actually, epsilon, I'm simply calling it as E. Okay. E1, E2 are available. So from that, we are having this M calculated. So M is nothing but methanol. Now, what is entering is getting coming as methanol minus other content. This is a methanol leaving. From that, M is calculated. So M is methanol entering, which is 11.29 mole. Like that. Now, you can also solve for this N2. Okay, before that, yeah, of course. Here, before that, okay, this you can solve actually. Because E1 and E2 are available. And yeah, see the 100 minus the other dry flue gas, other dry gases. So what are the other dry gases? There is this thing. That is equal to O2 and N2 of the dry flue gas. Say O2 and N2 of the dry flue gas. Service, we are writing one equation. So this is based on the first one. From that, we are getting M. Next, actually, we are going to solve for A. For that, we have these contents plus these two contents is equal to 0. That is what is given. That is this 100 minus these, that is simply equal to these two contents. So that is what is written here. So this is for O2 and this is for N2. So these together, now we are able to get this A, and E1 and E2 are already available. So from that, A is now solved. Or is now we are able to get how much of air is entering. So what is asked is percentage conversion of methanol. So what is the percentage conversion of methanol? Yeah, before that I am also solving for the excess air, because we know how much of air is entering and what is the O2 required. O2 required is actually the theoretical requirement is based on the complete combustion. So uh, methanol is supposed to go to CO2. So always you have to calculate the theoretical requirement based on the first reaction. So methanol entering is how much? It is M 11.29. So for 11.29, how much of O2 is needed? So one methanol is needing 1.5 O2. So from that, we are calculating this theoretical O2 required is 11 is M times 1.5. So this is a theoretical O2 requirement. Whereas how much of air is entering? Or this is air entering. Mm, yeah, this already we O2 required, and from that I am also calculating air required. How do you convert this O2 to air? Yeah, O2 available is 20, this is only 21%. So what is 100%? Okay, from that we are getting this theoretical air required. Whereas this is the O2 required, from that we are getting the air requirement. So air entering is already known, and air required theoretically is available. So air entering minus air theoretical divided by air theoretical will give you the percentage excess air. Okay, there is a thing we calculated. There is this second point we calculated. Now we can also calculate the water in the product gas. So raise the dry flue gas is leaving and water vapor is also leaving. How do you write this water vapor content? So I can as like this thing written, or as like this thing written for in terms of extent. We can also solve for this water. Water initially not there, water initially. So we have only this methanol alone is entering. So water is getting produced in this first and second reaction. So we can write this formula here. We have, of course, Ni naught is simply 0, and the extent of that is the first reaction is getting a production of 2E1. Second reaction from that we are getting 2E2. So that's why we have this H2 of the product is 2E1 plus 2E2. So E1 and E2 are available here, and from that I'm getting this water vapor content as 21.68 mole. So what is needed is, so we need to report the percentage of water in the product gas. So 21.68 mole of water is coming. And in terms of percentage, so this is already 100 mole and this is 21.68 mole. So 21.68, this is dry plus this is the water content. So this is the water content of the product gas in terms of percentage. That is water content of the product gas percentage, mole percentage of water in the product gas is 17.8. So that is from the dry basis data and from the reaction data. That is, we are writing these two reactions because of the availability of CO2 and CO in the product. And by writing this formula, we are able to get the values of M, there is a methanol entering, and that of air entering, as well as water leaving. And from that, we calculated the theoretical O2 requirement, which is based on the first reaction of complete combustion of methanol to CO2. So from that, theoretical O2 required is available, and theoretical O2 is converted into theoretical air, because O2 is only 21%. So what is 100%? From that we are getting this, and the excess air is what is entering minus what is a stoichiometry requirement divided by stoichiometry. So from that, excess air is calculated, and water in the product gas is how much of water is coming, and what is the total? Total is this plus this. So from that, water percentage is calculated. Now, the first point, there is a conversion, percentage conversion of methanol. So for that, conversion is what is entering minus what is leaving divided by what is entering. So we are having a feed of 11.29 mole. Yes, 11.29 mole is the methanol entering, and product is having a mole of 0.45. Methanol is also leaving unconverted. So methanol in feed minus methanol in the product divided by methanol in the feed. So that is giving the percentage conversion of methanol, okay, which is 96%. Now, the second part of the question, actually, for this 12 liter per hour, what is the rate of dry product gas and that of the water vapor? So, we have this 12 liter per hour, that we need to convert into moles per hour, because every data is available in terms of moles. No? So convert this liter per hour to mole per hour. For that, we are using this density data, density of the liquid. So from that, this is first converted into mass divided by molecular weight. From that, we have this molar flow rate. And already we know for 11.29 mole, this is for this mole, we have had a product dry gas of 100 mole and how much of water content. Now, whereas for this 297, what is the leaving gases? Simply scale it up. No, for this 11.29 we had 100 mole, and for 297 we have 297 into 100 divided by this much. So this is a dry flue product gas. Like that, water vapor also we can find. Okay, though the data is given, we are choosing a basis. The basis is to be chosen conveniently so that the calculation would be simpler. Though you can choose this as a basis, 12 liter per hour of methanol as a basis, but in that case, this data cannot be used easily. So, otherwise, wherever you have a complete specification, start from there. So here we have a good amount of specification that will help us to calculate M and A. And from that, we have uh, for this M, we have 100 mole, whereas for a new value of M, or is for this data of M, how much will be the dry content and how much of water vapor. So in that way only we are solving this. Otherwise, always choose a basis wherever you have a complete there is good specification, as well as that will also help you to solve the problem. Or is based on this product gas only we can easily find this methanol and oxygen used or oxygen entering. Okay, the new learning here is the extent of reaction method. Extent of reaction method, it is very good for solving these multiple reactions. Not only for multiple reactions, we can also use for a single reaction. So the formula is simply the moles of equal to what is initially present plus what is getting produced or getting consumed. Okay. Getting produced will be positive, getting consumed will be negative. So there is a stoichiometric question. We'll be using this negative signs for the feed and positive for the product. So there is a convention. Of course, this is well explained in our reaction equilibria part of thermodynamics in Smith and Vaness. Okay. So now I am available for any discussion on this. Otherwise, also you take a snapshot of this and try to do it yourself. So how much time left? Yeah, another about 10-15 minutes, we can see another simple problem. Okay. Okay. Of course, one more method I should also explain, what is called as atomic balance method. So here, in this atomic balance method, we don't write anything about the reactions. We simply make a balance on atoms of carbon, hydrogen, oxygen, and nitrogen. So because there are four atoms here, no? Carbon, hydrogen, oxygen, and as well as nitrogen. So there are four atoms, so you can write four balances and solve the problem without writing any reactions. We are going to see this problem. Okay. Say we know this dry flue gas, which is 100 moles. Of course, we have this N1 as unknown, and N2 will be simply 79% of A. Or is M is a unknown, A is a unknown. In addition, we also have N1. There is a moles of O2 in the flue gas, as well as W is also unknown. So there are four unknowns here. There is M, A, W, there is methanol entering, air entering, and water leaving, as well as O2 leaving. Of course, this N2 leaving is also unknown, but which is available in terms of A. There is 79% of A is N2. So in that way, we can say like only four unknowns. How many balances we can make? Theoretically, we can make four balances. One on C, one on H, one on O, and one on N2, or one on N. Okay, whatever. Okay, otherwise we can write four balances. Four individual species balances are four atomic balances. What is called as atomic balances. This atomic balance is a very easy, nice method. Of course, you may end up with more equations, but they are given the availability of a computer, you can easily solve. Maybe for an examination like GATE, you may have some little difficulty, but sequentially you can easily solve. Though there are four equations, you can sequentially solve. Let us see that. Say for the balance on C, how do you write the balance on C? What is how much of C is entering here? In 1 M, we have 1 C. So that's why C entering is simply M, and C leaving is in one CH3OH we have one C, here also one C, here also one C, whereas we have 0.45 mole. So 0.45 into 1, 9.03 into 1, and 1.81 into 1. So this is a balance on carbon. Like that, balance on hydrogen. In the 1 mole of M, we have 4 moles of, or is 4 atoms of H. 4 H is available. 4 H is available. So we have M methanol entering, and 4 in that 4 H is available. Okay, 4 into M, and the product is going to have, here we have 4 H. So we have actually 0.45. So 0.45 times 4, and this water vapor, 1 W is having 2 H. So that's why 2 W. So that's why in that way we written balance for H, like that balance on O. O is entering here in this methanol as well as air. So one methanol is having one O. That's why simply M. And here in the air we have 21.21 into A is your O2, but we are writing for O, so multiply by 2. So by that way we have 0.21 into A into 2. So this is a atomic oxygen entering in the air, entering as air. So there is air along with ethanol and air in the air. O2 in the air and O2 of ethanol. There is O of ethanol and O of air. They are written here like that. O is leaving here in this methanol and CO2. So here one is this is having 0.45 into 1. This is 9.03 into 2, because O availability here is 9.03 into 2. Here 1.81 into 1. And here it is 2 into N1. So by that way, and one water is having 1 O. So by that way, we are writing this balance on O. And like that, balance on N2 will be, so N2 is 0.79 of A is N2 is entering. There is here, instead of N balance, I am simply writing it as N2 itself, because whatever the N2 here is available as here. So I can simply write the balance on N2. By N2 entering is this much, and N2 leaving will be 100 minus all these contents. Or simply if you write like 0.79 A is entering and 0.79 A is leaving, that won't be a nice equation. Instead, you can write this in terms of 100 minus all these contents. So by that way, 100 minus all that content. So by that way, we are having another equation. So here we have A and N1 as unknowns. Okay, let us see now the equations. Balance on C, balance on H, balance on O, and balance on N2. So from that, we have 4 unknowns. Of course, 4 balances are available. So in terms of solvability of a problem, what we call as degree of freedom analysis. So number of equations are 4 and number of unknowns are 4. So you should have these equations and unknowns matching. Then only you can solve the problem. So the degree of freedom is simply 0. Actually, we should write like unknowns minus equations. Okay. Unknowns minus equation is the degree of freedom. Otherwise also okay. Here it is simply 0. So here we have this degree of freedom of 0, which means we can solve the problem. Okay, you can easily solve this, because in the first we have only M1 as the unknown. Once M is solved, then we can solve for W. And once M and W are available, you can get equation for A and N1. The other equation is also A and N1. So these two equations can be combinedly solved. So by that way, I'm getting this every unknown. There is A, W, and M calculated. Once these things are calculated, the rest of the things are similar to the previous one. Okay, otherwise, in solving for this material balance, we can make use of this extent of reaction method, or also use atomic balance method. Of course, atomic balance is much more useful whenever you don't know the reactions. Simply what is entering and what is leaving is given, you can easily solve the problem. Whereas for extent of reaction method, you should write the reaction and write this moles in terms of extent and solve for the problem. Okay.